Oh, you're smiling. You see me. Are we good? All right. We're going to get started with our next session. So we're really happy to have Kayla Shapiro, a production engineer from Facebook, coming in, and she's in Europe. So thank you, Kayla, for coming in. It's a little bit late over there. And you hear us, yeah? All right, welcome.
Yeah, loud and
so
clear.
Kayla's here to talk about how her and her team are working on establishing trust among Facebook's employees and systems. So with that, I will let Kayla take it away.
Cool. Thank you for the introduction. Hi, everyone. My name is Kayla, and I'm a production engineer at Facebook. I hope you're all enjoying Authenticate, either in person or remotely like myself. I'm curious as to what the spread of time zones might be for folks joining in, but it's just turned about 10:30 p.m. here in London, and it's pouring rain outside. I wish I could have joined in person, but we'll have to make do with what we've got. So my team is called PE Employee Authentication, where the PE stands for Production Engineering, and we are based primarily in London. And today I'm going to talk to you a bit about the work my team is doing to help secure employee access to production environments and establish employee trust. So let's kick off with an agenda. I'll start by giving some background on why my team exists and the high-level goals we are trying to achieve. From there, I'll dive into 3 distinct problems we are working on in employee authentication related to establishing employee trust. And then we'll wrap up with some key takeaways. So I'll start just by giving some background on what my team is working to achieve. So on PE Employee Authentication, our mission is to provide an easy, robust, and secure platform for employees to use from their devices, so phones and laptops, so that they can obtain the identities required for securely accessing production resources. But why? So 2020 fundamentally shifted our lives and the way work is done at Facebook. With the company evolving to support fully remote work, it's become even more imperative to be intentional in how our employees access production resources from external environments, such as our corporate network, over the internet, and from the public cloud. Historically, we've had several ways of communicating with our production resources, and these implementations have been left to owners of a particular application or client. And this can have pitfalls. The first being that when security isn't well defined, it tends to be implemented everywhere. And as an example, at work, we tend to see evidence of this in the number of 2-fact checks we have pop up in our day-to-day work as engineers, generally more than is necessary. Second, this doesn't guarantee a solid, well-defined security model and is bound to lead to holes that can be breached. Practices like storing identities plainly on disk or using phishable authentication methods can lead to exfiltration of employee auth proofs, which can then be used by nefarious actors without us noticing. And all of these points kind of lead us to our ultimate why: wanting to maintain the trust of our community of users. In the past few slides, I've thrown around the word trust a lot. After all, this presentation is called Establishing Employee Trust. You may have heard of a paper by Ken Thompson called Reflections on Trusting Trust, which details how we can't trust any of the code that we did not totally create ourselves. And this includes things like dependencies, compilers, anything in the software supply chain. Thompson also says in a subheading that perhaps it's more important to trust the people who wrote the software. So how can we trust each other? I'm under the impression that this is a very hard problem to solve, and I don't mean that philosophically. But to put it simply, we use technologies and build software that enable us to make use of digital identities that let us start to trust that person or machine is who they say they are. With 2FA, for example, this can come in the form of Touch Bar on macOS, RIP, hardware-backed tokens, or phones. And on laptops, we can use things like Kerberos credentials or certificates. The main thing is that these identities enable users and clients to authenticate to services offering an identity that says knock knock, and services to authenticate to clients saying, you've come to the right place. But not all authentication methods were created equal, and some go out of fashion. But the important things to consider are the methods by which these identities are established and how these identities are obtained. Because if one can be stolen or improperly issued, the game's afoot. Now, let's dive into 3 distinct problems my team is solving to close the gaps in our ability to establish employee trust. First, on the left, we have key exfiltration. Certificates are used all over the place for things like mutual TLS or establishing SSH connections to internal services. Historically, these public and private key pairs have been stored plainly on disk and thus susceptible to being copied. And if this is possible, how can we trust that an action actually came from a Facebook managed device? The second problem in our stack is in the issue of two-FAC. Two-FAC is designed to detect that you are physically present at your machine, yet ironically, things like SMS or HOTP tokens are phishable. And if a token can be phished, how do we know that this action came from you? And finally, the third problem we are working on is in the scope of data integrity, and specifically for our use case, key transparency. I'll talk a bit more in depth about what that is down the line, but the gist here is that if data can be altered undetected, such as a database full of keys associated to a device or employee, how can we actually trust that the key presented belongs to you? So yeah, this is the scope, and it's quite large for a team of 6, but it's also quite fun. So let's dive into preventing key exfiltration attacks. As I mentioned previously, certificates are very commonly used in our infrastructure to establish some sort of identity. I'd wager that it's probably our most common credential. Authentication, especially mutual authentication, is an important aspect of secure systems. Using two-FAC, our employees can fetch certificates to talk to various services and perform certain actions. These certificates are bound to the user identity via a cryptographic key pair, the private portion of which is used for signing. We can save talking about PKI for another time, but essentially given a trusted certificate authority used to issue a certificate, we can verify that we are talking to an intended host and not some Mallory in the middle. And with this, we can establish secure connections. But as you may have noticed, secure in that last bullet is scare quoted, because what happens if the private key ends up in the wrong hands? To solve this, my team has built a platform. And that platform is SKS Agent. SKS here stands for Secure Key Storage, because SKS Agent utilizes secure crypto processors to achieve the following goals: preventing key exfiltration attacks, leveraging the one-to-one mapping of employee to device ownership to use an employee's device as proof of something they have for two-FAC authentication checks, and providing APIs for engineers to leverage hardware-backed certificates in facilitating their connections to production resources. On initial startup, which is kind of just a daemon running in the background, generates keys within hardware security chips. Instead of storing identities on disk, the agent leverages Secure Enclave on Apple devices and TPM on Lenovo's to store private key information. These chips are isolated from the main processor and encrypt that private key information, so even if the device itself gets compromised, keys can't be exfiltrated. These keys that get generated are then used to fetch certificates from the CA for the device that they exist on. But how do we know that a particular key belongs to a particular device? There's a manual step involved in which the owner of the device must enroll the keys SKS agent manages into a public key registry, at least public for the company. This enrollment process creates a mapping between a device's serial and owner combination to the unique, secure, private key. Enrollment requires two-FAC and for the device to be officially assigned to its owner. So while we could go down the rabbit hole of trust in this process, for the scope of this talk, we'll consider it fairly secure. With an employee's keys enrolled in the key registry, we can now include extra information in our certificate signing requests so that the CA can verify the key's ownership and signature and decide whether or not to issue a certificate. So now that employees have these secure hardware-backed certificates, how can they use them? Let's start with a diagram. At the bottom, we have the hardware security chips in which the keys are generated. Above that exists a set of OS-specific APIs for performing operations on the secure hardware. For Mac OS, we use C, whereas for Linux and Windows, we are able to use pure Go, which is the dream. Above these APIs and at the bottom of the SKS agent stack lives our SKS library. We're in the process of open sourcing this, but not quite there yet, so it'll be available soon. As a reminder, SKS stands for Secure Key Storage, and this library acts as the heart of the operation and is a generic Go wrapper for the different operating systems, which, yes, means compiling CGO for macOS releases. On the other hand, the brains of the operation is the agent itself, which handles key creation and deletion, as well as certificate fetching and renewals. But this slide is called Libraries and APIs to Integrate with, and we haven't really talked about that. SKS agent implements the SSH agent protocol and exposes a Unix domain socket, by which SSH can establish secure connections using SSH certificates backed by securely stored keys. On top of that, we have implemented an extended SSH agent protocol representing the various functionality in a PKCS11 interface, built as a C library that allows Go code to become a PKCS11 authentication token. And for those of you unfamiliar with PKCS11, this interface is a cryptography standard that defines the creation and manipulation of these tokens where the secret is a cryptographic key, which basically means that this library can be leveraged by applications to perform cryptographic operations, such as using certificates for TLS connections. Now, one of the things I mentioned in our team's mission was the creation of a secure and easy platform. So not every engineer wants to load a CDLL into their application. So we've also done the work of abstracting this away for ease of use. It's always important to remember as someone working in security that while locking things down sounds very exciting to us, others can see security measures as roadblocks to circumvent in order to make their own work lives easier. So balancing security with ease of use is key. So what have we achieved with all of this? In addition to integrating tooling with SKS Agent, the daemon also supports renewal of certificates via two-FAC in the background. It also manages all of the logic around establishing SSH connections to jump hosts. And with this, we conclude problem number 1, which brings us to two-FAC. What's the problem with two-FAC? Well, to start, not everyone loves it. And what do I mean by that? Well, on employee authentication, we sometimes see folks take, and I'm not sure what the best word here is, but hilarious actions to circumvent security measures in place. Not for any nefarious reasons, but generally because they are tired of decentralized two-FAC checks. And these can be silly things that look on the order of, say, automating the insertion of a password. Then there's phishing. As I said previously, two-FAC is generally meant to detect that someone is physically at their machine. But many two-fact methods suffer from being phishable. And this is something our red team loves to exploit, especially during Hacktober. And since two-fact checks can be scattered all over the place, we can be left open to compromised credentials. Also, I don't know about you, but I would need extra hands to count the number of times that I've accidentally tapped my YubiKey and nearly sent an HOTP over chat. To solve this problem of trusting two-fact user presence, we turn our attention to FIDO2. So in the case of FIDO2, my team is both working on centralizing two-fact checks to reduce the number of reauths that engineers see, and also facilitate the transition from HOTPs to FIDO2 authentication. But why FIDO2? Given the sponsors of the conference, I assume a lot of folks in the audience will have a working knowledge of this spec, but we'll still go through some key advantages. To start, FIDO2 is based on public key cryptography. So when you trigger your FIDO2 authenticator, you are actually signing a challenge. FIDO2 also has support for attestation, meaning that we can distinguish between vendors and models of keys, which can be extremely powerful in the event that we find we need to block hardware where vulnerabilities have been discovered. There's also support for browser-based phishing protection, and in terms of convenience, FIDO2 opens us up to the world of passwordless authentication, which not only makes things easier on users, but limits the risk of weak or repeat passwords. And going with this, there's also the potential for user verification, which can be optionally used. You can see an image of a PIN prompt on this slide. We could basically have that pop up each time a signing request is issued and force the user to enter a PIN. Something like this would have to be implemented pretty carefully though, because as I've said, we want to make things easier on users. But if, for example, we had some highly sensitive operations, we could ask the employee to input a PIN. And this also protects against theft of a hardware key, as the thief would need to know the PIN to use it. So what does this look like? This is from the FIDO Alliance website, if you want to read more about it. But in terms of registering a FIDO2 authenticator, this diagram shows a smartphone, but this could easily be a YubiKey plugged into your machine or a touch bar on your Mac. In the case of registration, if more than one authenticator is plugged into the machine, the user will be prompted to choose an authenticator. Then they'll be asked to do some sort of physical gesture, such as a tap. And at this point, the authenticator creates a cryptographic key pair inside it, and only the public portion is sent to the server and stored in a database. Our FIDO2 authenticator enrollment flow looks fairly similar to this, but the required enrollment process requires a user to reauth with some other form of two-fact to establish the employee's identity. Authentication looks very similar. In this case, the server sends cryptographic challenge containing the previously registered key. The user again makes some sort of physical gesture to establish their presence and improve the request. The authenticator then signs the challenge with its private key, and the server verifies the signed challenge against the public key stored in a database. And this is kind of where we really see the relation to public key infrastructure and how FIDO2 authentication plays out. Now, what you may have noticed in this and the previous SKS flow is that the public portion of keys that get generated ultimately get stored in a database. But how can we trust that the data in that database is legit? That I myself have not tampered with it? And this leads us to integrity. We saw this image previously on the slide where I talked about SKS agent and the keys that get enrolled into a key registry. When storing these keys in a database, there is a risk of tampering. Anyone that can get onto these physical machines could go and enroll a security key without someone's knowledge. So we need to mitigate this. And we do so with something called key transparency. The idea behind key transparency is to build an append-only log. So in this case, we aren't saying that this solution is tamper-proof, but rather tamper-evident. So if an action is taken, we can audit it and do something. This, in turn, is built upon a technology called a Merkle tree. A Merkle tree is basically a binary tree of hashes, and it greatly reduces the amount of data a trusted authority needs to maintain to prove data integrity. It also separates the validation of data from the data itself. The proofs required to prove data integrity are also easy and fast to compute. If you do go on to read more about Merkle trees after this talk, you'll notice that there is a lot of content online around its use in blockchain technology, as well as in things like verifying file contents. But all of this is a bit abstract. So to illustrate how a Merkle tree works, let's go through an example. On the bottom here, you have some data. This data can be anything, but for our team's use case, it's the public key information that is being enrolled. H is a cryptographic hashing function. And when constructing a Merkle tree, you start by hashing the data in each independent leaf. A level above this, you would then concatenate these two hashes together and then hash the concatenated data yet again. So what makes this append only? Well, we could take another record, C, hash it. In this case, since there's no other records next to it, we'd propagate it up a level and hash it with the other hash from level 1. And then we can take leaf D, hash that, update level 1 again, and then update the root, and so on, and so on. Ideally, the hashes are collision-free and deterministic so that no two plain text hashes can be the same. And we move this way conceptually from left to right, where each hash is a hash of the child nodes. And this dense property is what makes it append-only. Okay, so given some data, how do we prove its inclusion in a Merkle tree? I've simplified the tree a bit here, but let's say I have my key, which is really leaf B. And I've presented my key for verification of its enrollment in the key registry. In order to validate the inclusivity of leaf B, we just need the bits of the tree required to traverse and construct the root node. With the root node constructed, we can then compare it to the source of truth root node and see if it's the same. So we don't need everything here to traverse to the root node. What we really need looks more like this. If we start at B and work our way upwards, its left sibling is A. And to construct the parent node of A and B, we first compute the hash of B and work our way up with the necessary information to construct the root node, similar to how when the tree is created. And we can verify that this root node that we've constructed matches the known root node. And then ultimately, if ultimately the tree grows, we just have another level by which we need to construct the root node, where the height of the tree is log n, and n is the number of nodes. So what does this give us? For one, it gives us auditing. It would allow us to audit and understand what's changed. And this doesn't have to be, like the security team's auditing, but it could also be users. For example, a given user could have a view of their enrolled security keys, and we could allow this interface to show a history of every key added or removed with the date and time of when they were added or removed, and have this be cryptographically secure. We could also have some sort of auditor daemon, something that notifies you when a record is added or removed. Kind of like how Apple does when you add a new device to your iCloud account. So there are several ways in which this could be leveraged to audit actions taking place. And with this, we are on the path to trusting our data. To conclude, can we trust each other yet? We're getting there. There's no one-size-fits-all solution to establishing employee trust. Rather, specific authentication problems require specific technologies to solve distinct problems that close the gaps that could lead to breaches in trust. Further, trusting a user means trusting your source of truth. It's not enough to have the strongest authentication methods in the world if you can't say with confidence that the data that backs those methods is stored securely. And finally, I want to reiterate the importance of balancing security with ease of use. And thankfully, passwordless authentication is an awesome selling point when devising strategy around building secure systems. And finally, thank you very much for your time. I hope you enjoyed the content. I know I covered quite a bit. I also want to thank the FIDO Alliance, the conference sponsors, and the organizers of Authenticate 2021 for the awesome job they've done putting this conference together and for their support in virtual attendance. And then also a thanks to my teammates for all of their dedication and hard work in shipping these projects. So yeah, thank you.
Thank you so much, Kayla. Does anyone have any questions for Kayla? I had one in the app I just wanted to ask you, which is, do you have any, well, first they said it was a great presentation, so thank you. I concur, it was great, thank you.
Thank you.
Is there anything you could point folks to in terms of any further, details, like published details about what you're doing that they could reference to help them with their own deployments?
So at the moment, I don't think we have anything published, but as I mentioned, we're going to be open sourcing our project soon. And if anybody, wants any tips, they can feel free to add me on LinkedIn. Just search for Kayla Shapiro and Facebook, and I'll show up.
Thank you. Oh, we do have a question in the room.
Hi, great presentation. I had a question on, when you had the slide on code signing, I noticed that you get prompted to sign, but it isn't actually telling you what you're signing. Is that a thought, or what was the thinking behind that? Is that just a thing to do in the future, or not necessary? What are your thoughts on that?
Yeah, so this is something more down the line that we're going to be implementing. But yeah, essentially, we would want to have a bit more of an informative prompt about, where the prompt is coming from, what it's for, so that whoever's tapping it has knowledge of it and thinks and understands that they're the one that's executed this action. Does that answer the question?
Yes, it did. Thank you. We have another question for you.
Thank you for the great presentation. I have two questions. One is, how do you protect the APIs? You mentioned on, I guess, slide 4 or 5. And the second one...
Yeah. Sorry, go ahead.
And the second one is, if someone inserts a key directly into the database, will the hashing calculation fail?
Both of those are excellent questions. So the first one, protecting the API. So as I mentioned, with the agent, we have a Unix domain socket that can be used to communicate with it. And we do have authentication around the socket. So the idea being that, not just everyone can connect to it. We kind of have some special considerations to ensure that it's only Facebook deployed applications that are able to do so. And then on the second question about inserting an entry into the key registry, if someone were to do that, it would not necessarily fail because it would be appending to the log that we have. But ideally, what we'll have in place and what we have in place is to have triggers that would notify that a key was created for a specific employee to ensure that the entry was intended.
Cool. Thank you.
All right. Thank you so much, Kayla, for coming in. I know it's late. We really appreciate it. And thank you for the great presentation.
My pleasure. Thank you for having me.
They're all clapping. I know you can't hear them, but they are. All right, so next up.